In our last unit, we were talking about electrostatics, and that was all about the forces and fields and potential for work to be done. So, what we're going to look at in our next unit, electrodynamics, is instead of having a bunch of things that are stationary and remain stationary, what happens when things are able to move? What kind of changes in position and motion do those things that we talked about, what does that actually cause? So first thing we want to jump back into is voltage. It was the end of the last unit, first thing in this unit. So voltage is a really important thing for us. Anything that's battery powered, like flashlights, and I don't know if anyone uses battery powered clock radio anymore, but if you do, that operates on chemical energy. So batteries, they're made up of two different substances. Totally depends on what kind of battery you have as to what's inside it, but that's something more along the lines of what you would talk about in a chemistry class. We don't need to know how to make them, just what do they do, how do we use them. So that chemical energy is actually separating charges in a battery and creates a potential difference, the thing that we talked about right at the end of the last unit. So to separate these charges and create the positive and negative terminal, a battery has to do a certain amount of work on those charges. And that work per unit charge is called the voltage. Voltage, V. So still using V to talk about voltage. We could also call it the electromotive force, or EMF. You may also see, oh no, hold on one second, I tried to copy something and it didn't. Okay, I got it this time. So you may also see electromotive force written as EMF or a lowercase epsilon. So anytime you see any of these things, it's the same as V. And we're still measuring in volts. None of that has changed. So remember that 1 volt is the same thing as 1 joule or 1 coulomb or 1 J per C. That voltage has the same units that potential difference did. And that's really because, they mean the same thing. The voltage of a battery, whoa, is just, that's the worst, how much work was done in setting up a potential difference between the positive and negative terminals. Man, it's been a while. I need to stop taking these breaks. We were talking about energy, one of our other field forces. So if we lift an object in the air, we give it a certain amount of gravitational potential energy. So the work and gravitational potential energy are both measured in joules. So the amount of work that you do in lifting some object up is exactly the same as the amount of gravitational potential energy that it gains. So a battery here would be kind of like if you had some kind of elevator or escalator or portal that you could put some object in and it would automatically be, up at some certain amount of gravitational potential energy. To play for us here. Well, when you have a current, which we'll talk about a little bit later, flowing around a circuit, then we say there's a certain voltage drop, or we might call it a potential drop, across the circuit. So the battery provides all this energy for things to move around in the circuit. But each different component that you have kind of uses up a bit of that energy. So that's what we're going to care about. We care about how much is each element actually using here. The current is actually taking all that potential energy. So you do some work to store energy in a battery. The current takes that energy, turns it back into work. So it's trying to move these things from a high potential over to a lower potential. And exactly how low is that potential going to be? Well, if you have, say, a 30-volt battery, then the current has to drop 30 volts. It has to drop down to 0 to send all those electrons from the negative terminal of the battery over to the positive terminal. So that's going to be something that's really important for us to remember later on, that we have to drop all the way down to 0 in one loop around a circuit. What is a current exactly? When you have a wire that connects the two different terminals of the battery, the positive and the negative, then the potential difference across the battery actually creates an electric field in the wire. So electric fields we talked about a lot last unit. The electrons that are at the negative terminal are able to move through the wire over to the positive terminal because of that electric field. They move along with the electric field lines. So remember, it's electrons that are moving and not the positive charges. The electric field generated in the wire by this battery would point out away from the positive and in toward the negative. But remember that the electric field, we tend to draw it for a positive test charge. Since it's the electrons that are actually moving, they'll go in the opposite direction. So they're going to go out from the negative and around the circuit into the positive. So the electrons are moving from negative to positive, like this, from the positive terminal to the negative terminal. The electrons are actually able to move pretty quickly. The only problem is that their movement is pretty random, and they're always running into other electrons, positive charges, the edge of the wire. So overall, even though each one is moving quickly, we don't see a very, fast overall speed. Each electron is moving through the wire toward the positive terminal at a speed v, v sub d. And that sub d stands for drift. So they move with a drift velocity towards the wire. So we're only considering how much closer they're actually getting to the positive when we talk about drift velocity. How fast are they actually moving around the circuit? And that's really small. It's like 1 millimeter per second. Really, really tiny compared to how fast they actually are. But considering how many electrons actually are in this wire, it'd be really stupid to follow just one electron around the circuit. So we look at the overall from all of the electrons moving, and that's what we call the current. So all the electrons moving together create a current, and current is just the amount of charge per unit time across an imaginary plane in the wire. So let's say we just, snipped a little section of the wire off, and somehow, which it's not possible, all the electrons were able to just, pour out of it, kind of like a garden hose. Then however much charge you have coming out of that hose in a certain amount of time would be the current. equation form? Well, the variable that we're going to use for current is capital I. Current equals, well, we said it's charge per time. Our variable for charge is Q. Our variable for time is T, just a charge per time. So let's see, what is that going to do to the unit? All right, so we know charge is measured in coulombs. We usually want to measure time in seconds in physics. So we have a coulomb per second, but you're more likely to see it called an ampere, or A, capital A. So 1 coulomb per second is equal to 1 ampere. So it seems pretty simple, right? The currents flow around, it's like a hose, so they create this current, and physics just can't ever let anything be easy. Not ever. Why do we do this to ourselves? Let's talk about the direction of the current. So even though the electrons are little charges, they're moving from the negative to the positive, the current actually flows from positive to negative. So how can electrons move one way and current goes the other way? That doesn't even make any sense. It's pretty strange. But let's take a look at this example. So let's say we're going to set a bunch of chairs around in a circle. I guess 12 is the magic number here. And we have 11 people sit down, obviously leaving one chair empty. So if we went, one person at a time, so the first person, whoever is beside this empty seat, slides over one seat, they would create a new empty seat. So the next person moves into that empty seat. That person moves into the new empty seat. And we keep going around like this, like we actually did or are going to do in class, depending on if we do it tomorrow or not. Then even though the people, which represent the electrons here, are moving clockwise around the circle, how does it look that the empty seat is moving? Well, great question. The empty seat kind of goes in the opposite direction. You can see here it starts kind of in the 2 o'clock position, moves to the 1 o'clock position, moves to the 12 o'clock position. So that's definitely counterclockwise. So even though the electrons move in a clockwise direction, that empty seat is moving counterclockwise. So the empty seat here kind of represents some way of visualizing the current. And the last thing for today is to talk about resistance and Ohm's law. So you already know that some materials conduct current better than others. We call them conductors. Metals are the best ones. You already know that. So if we had a copper wire and a glass wire that, were identical sizes, same length, same cross section, and we put the same potential difference across them, or, hooked them up to the same battery, then the current in the copper wire is going to be a lot bigger than what it is for the glass wire. And that's because, copper, a conductor, is able to let its electrons move a lot more freely than glass would be. So we say that glass has a higher resistance than the copper wire. And resistance, we use the symbol capital R to stand in for resistance. So we can actually express resistance in terms of our potential difference, or our voltage, remember, and the current that we just talked about. So the potential difference you apply to some material and how quickly the electrons are able to move through it. If we wanted to put this into equation form, then the resistance of a material is just a ratio of the potential difference you apply and how quickly the electrons are able to move through it. So R equals delta V over I. Usually we'll leave out the delta and it's just R is V over I. Ohm's law actually makes it a little easier to remember than R equals V over I. Not that three variable equations are really that difficult. So for any given voltage, so some voltage, the bigger the current is, the faster electrons are able to move through it, then the smaller its resistance is going to be. And the same works backwards. So if you have a really small current flowing through something, that means it has a really high resistance. So how are we going to measure it? Our unit for potential difference is just the volt. So if we have 1 volt divided by unit for current is amperes, so 1 volt divided by 1 ampere is going to equal 1 ohm. The unit for resistance is called an ohm, but we don't actually write out ohm every time. We use the capital letter omega. So 1 volt over 1 ampere is equal to 1 ohm, that little symbol there. That equation that we just developed for resistance is actually just an awkward way of talking about Ohm's law. So we use Ohm's law to relate those three important quantities that we have set up. So we just got current and resistance and voltage from our last unit. So the three different ways that we have to represent Ohm's law is V equals I times R. We could also say that R equals V divided by I, and the last one would be I equals V divided by R. So these equations tell us how we can maximize a current if we look at this last one. To get a big I, we could either have a really big V or a really little R. So by having a large potential drop and a small resistance, we'll maximize the current. And that's one of the most important equations that we're going to have, in this unit, and even through, well, our next unit will be just magnetism, so the unit after that. Let's take a look then at Ohm's law in action. We have 3 batteries being added to a circuit, which multiplies the potential difference in the circuit by a factor of 4. A resistor is also added, which doubles the resistance of the circuit. So how is the current in the wire affected? So we want to look at what happens to I. So we'll use the I equals V divided by R version of this. And in our base circuit, we could just say that current in the base circuit would be V divided by R. Now let's make some of these changes. So I'm going to call this one I2 since we're changing the circuit a little bit. So our potential got increased by a factor of 4. So we'll have 4, whatever the original V was. Divide that by how much did our resistance change? Doubled. Alright, so that looks like it's going to simplify to 2V divided by R. So all these changes that we made just doubled our original current to I. Not too bad, right? all these things have different resistances, though. We looked at copper and glass and wood and all the other things that have all these different resistances. But what actually affects how resistant something is to allowing a current to flow through? And that's where we get into talking about resistivity. So, resistivity for which we can use the symbol rho. Oh yay, another rho. Wonderful. The resistivity is a property of each material that affects how good of a resistor it is. So if you have a really, really high resistivity, you have a really, really high resistance. So resistance actually depends on the dimensions of the wire as well. So on its length L and its cross-sectional area A. So the resistance of some material, I need to get my rho back, is equal to rho times the length divided by the area. So if you have a really, really long wire, we increase L. What's that going to do to the resistance? Well, if L gets bigger, then R gets bigger because the charges have farther to go. If we increase the cross-sectional area, though, then we're going to reduce the resistance because it's a lot easier for the charges to move through. You can kind of think of it like the hallway between classes. So let's say after physics, your next class is on the other side of the school building. Well, you have a really, really long hallway to walk through and a whole lot of people fighting you to get to their classes as well. So the longer it is, the longer it'll take you to get there. But if we took those hallways and made them really, really wide so that people could spread out a little more and get out of your way while you book it to your next class, then you'd have a lot easier time getting there. If we wanted to talk about the unit for resistivity, so what is the unit for rho? Well, we know we want to get out ohms. Length would be in meters, area would be in meters squared. So to get meters to go away, we would have to have ohm times meter. So unit for resistivity will be the ohm meter. And to bring back the examples that we've been using, the resistivity of copper is about 10 to the minus 8 ohm meters, and the resistivity of glass is about 10 to the 12 ohm meters. As you increase the temperature, the resistivity increases. You have a lot more interaction from all the charges that are in those metals. But for the most part, these are things that you could look up in a table like the one at the link in your notes. Also in the textbook, they are all over the place. Just Google it. Next example is going to be about resistivity. We have a copper wire that's 4 meters long and has a cross-sectional area of 10 millimeters squared, and it's connected to a battery with a potential difference of 9 volts. We want to know what is the current that runs through the wire, and we're going to assume the resistivity for copper is 10 to the minus 8 ohm meters. Okay, we want to figure out a current, so we know we can jump back to Ohm's law and say that I is equal to V divided by R. I'm pretty sure they gave us a V in this problem. Oh yeah, right here, 9 volts. So now we just need a resistance, and oh, it's not in this problem. So we are actually going to have to use this information about the size of the wire and its resistivity to figure out what it is. So the resistance for this specific wire that's 4 meters long and has a cross-sectional area of 4 millimeters squared will be, we take our resistivity, 10 to the minus 8 ohms times meters, and we're going to multiply that by the length, 4 meters, divide it by 4 millimeters squared, but we have to get that into meters. If we divide by 1,000, that would give us some really strange kind of like millimeters, I don't even know. But since it's squared, we have to divide by 1,000 twice to get rid of both of those. So we'll do 4 times 10 to the negative 6 meters squared. So our resistance here will be 0.01 ohms. Alright, so we have the resistance now. So we can jump back into this equation we wanted to use originally to figure out what the current is. So we know we have 9 volts because that's the potential difference of the battery. We know now that our resistance is 0.01 ohms. So what are we looking at here for a current? 9 divided by 0.01, a current of 900 amps. And just last tiny little thing is about conductivity, which is really unlikely that you would hear about this. It may be some random little test to see who's learning what, but we can also talk about a material's conductivity and conductance rather than resistivity and resistance. So just like it suggests, it's just the inverse of each other. So instead of how easily can things flow through, how difficult is it for things to flow through? So if we say that a material has a high conductivity, that's another way of saying that it has a low resistivity. So high conductance, low resistance. And I know sometimes when we assign variables or name things, it's not exactly intuitive, but it kind of does work out right in this case. So someone with half a sense of humor named the unit for conductance the mho, or just an inverted omega, which we use to represent resistance. So since conductivity is the inverse of resistance, we invert the symbol or write it backwards. He could have done a better job with that one. And we have conductivity.